Hello children. Today I am going to continue with the numericals of Biot-Savart law. So I am going to get into my first question. So what the first question says, a current of 1 ampere is flowing in the sides of an equilateral triangle of side 4.5 into 10 power minus 2 meter. Find the magnetic field at the centroid of the triangle. So once again I am going to read out, a current of 1 ampere is flowing in the sides of an equilateral triangle of side 4.5 into 10 power minus 2 meter. Find the magnetic field at the centroid of the triangle. So you can focus on the board. You are able to see I had drawn an equilateral triangle ABC. What about the centroid? Centroid of the equilateral triangle is O. Can easily say O represents the centroid. At O, what will be the magnetic field when a current I flows through this loop? So let us suppose that a current I flows as marked in each side. I'm going to assume a current I flows as marked in each side. Now, obviously since the figure is a symmetrical figure, let us check the direction for each side of the triangle. So I'm going to use my right hand thumb rule for the side AB. So if I'm going to keep my thumb along the direction of the current, that is AB, the fingers at O acts outward. So you're able to see what about the direction of magnetic field due to AB at O will be outward. Similarly, I can say for the arm BC and also for the side CA, the magnetic field magnitude wise they are equal and also they are acting in the same direction. So just by getting one side value, I'm going to multiply it with 3 to get the total value at the centroid. So let us start. What is the contribution due to the side AB? I am going to determine. So let us first generate a general formula, then we can apply the values to get the answer for the question. Now what about the magnetic field due to the part AB? What is the formula for a finite straight conductor? Already we are discussing it is mu naught by 4 pi I by, what about A, the location distance? I'm going to mark OD will be the location distance. So it will be I by OD. It is sine. What about the angle? Since it's equilateral triangle, phi 1 will be 60 degree. Phi 2 will also be 60 degree. So what I can write is sine 60 plus sine 60. Now, what is the thing that is unknown in this question is OD. So OD can be obtained by this right triangle. So I'm going to assume if the edge length or the side is A, if I'm going to say the side of the triangle is A, similarly this part AD will be A by 2. The part AD will be A by 2. So we're able to see a right triangle ADO. So from right triangle ADO, I can use tan 60. So what is tan 60 comes to be? Tan 60 is AD by OD. Tan 60 is AD by OD. I want OD. So it will be OD is equal to AD by tan 60. So what I can put is AD by tan 60. What is AD? Already we know AD is A by 2. A by 2. Tan 60 you know it is root 3. So if I'm going to make it is A by 2 root 3 will be the value for OD. So I can put it back here. What will happen? BAB is equal to mu naught by 4 pi into I by A by 2 root 3. The 2 root 3 moves up by A. What is sine 60 is root 3 by 2. Another sine 60 is root 3 by 2. It will be 2 root 3 by 2. So what I can write is 2 root 3 by 2. So you are able to see this 2 cancels off. On reduction, mu naught by 4 pi, you are able to see root 3 into root 3 is 3, 2 3s are 6. So what I can write is 6I by A. So this is the contribution of one side of the equilateral triangle. This is the contribution of one side of the equilateral triangle. But already I said, what about the total contribution will be 3 times. So what will be the final value I can write? What is magnetic field at the centroid will be mu naught by 4 pi into 6I by A into 3. So it becomes B is equal to mu naught by 4 pi 18I by A. It will be 6 3s are 18, 18I by A. So this is the generalized formula for magnetic field at the centroid of a equilateral triangle. So what the question says, what about the current flowing in the triangle is 1 ampere? What about the value of A? Side is 4.5 into 10 power minus 2. I can put it back to get the final formula. So before this, I'm going to recap the entire derivation. So our aim is to find what is the magnetic field at the centroid of the triangle. So as the diagram clearly says, I'm going to use the direction rule for the arm AB. You are able to see the magnetic field is outwards. Similar is the case for the other two arms BC and CA. So just by getting one side value, I can multiply it with 3 to get the total value of magnetic field at the centroid. For that, I'm going to calculate the magnetic field for the side AB. So what about the magnetic field for the side AB? It will be similar like this. Obviously, it is a finite length and the location will be at the center. So what is the formula for this? It is mu naught by 4 pi I by A sine phi 1 plus sine phi 2. So here I change the value as per the question. So mu naught by 4 pi I by, what about this observation point will be OD. Observation point will be OD. So I'm writing I by OD into, what about the angle phi 1 and phi 2 is 60. So I'm writing sine 60 plus sine 60. Now the only unknown is OD. So how to get OD? From the right triangle ADO. What is tan 60 is AD by OD. OD can be written as AD by tan 60. AD is already from the figure A by 2. Tan 60 you know root 3. So what I'm going to get for OD is A by 2 root 3. Put it back on the main expression. What I'm going to get the reduced form is mu naught by 4 pi 6I by A. This is only for one side of the equilateral triangle, but I want the total contribution due to the 3 sides. So just multiply this value with 3. So what is the value I'm going to get is mu naught by 4 pi 18I by A. Now as per the question, what are the two values given to you? I can put in the main equation. What is the main equation once again? It is mu naught by 4 pi 18I by A. Put the value. So B comes to be mu naught by 4 pi, you know it is 10 power minus 7 into, what about I? I is 1 by, what about A? A is 4.5 into 10 power minus 2, it moves up. So I'm going to write it as 10 power 2. Now what I can write, do the simplification, B is equal to 10 power minus 7, 2, it will be 10 power minus 5. 40, once again it is 18 by, it can be written as 45 by 10, the 10 moves up. So what is 18, 45? 2 6 are 18, 3 6 are 18, 15, 2, 5. So you are able to see 2 by 5, it is 0.4. So you are able to see it is 0.4 into 10 power minus 5, 1, it will be 10 power minus 4. So if I'm going to write it in the normal scientific notation, it is 4 into 10 power minus 5. The magnetic field unit is measured in Tesla. So what about by putting all the values? The magnetic field at the centroid comes to be 4 into 10 power minus 5 Tesla. Let us get into our next question. So what the question says, a hexagonal loop of a metallic wire, each side A carries a current I. Find the magnitude of magnetic field at the center of the loop. So once again, just now we did for a triangle. The question is repeated for a hexagon. The pattern we are going to use the same. So you are able to see the diagram, hexagon. Let a current I flows as marked through each side. So obviously you are able to see the current flows as per the arrow marked. Here also I am going to say, as it is a symmetrical figure, what about the magnitude and the direction of magnetic field at O due to each side will be same? What about the magnitude and direction of magnetic field at center O due to each side of the hexagon will remain same? So what I can do, I can get one side value and I'm going to multiply it with 6 to get the total magnetic field. So for reference, I'm going to take my side as AB. DB the midpoint, OD is the observation distance. So once again it is a finite length conductor, and you know the formula for a finite length conductor, B is equal to, BAB is equal to mu naught by 4 pi I by A is OD once again, A is OD sine, since it is a hexagon, obviously the two angles will be 30 degree. The phi 1 is 30, phi 2 will also be 30. So it will be sine 30 plus sine 30. So here also the only unknown is OD. So once again I am going to use the same tan formula. So you are able to see what is tan 30 from that triangle. Tan 30 is AD by OD. It will be AD by OD. So I want OD. OD will be AD by tan 30. What is AD? Once again AD is A by 2. AD is A by 2 and you know tan 30 is 1 by root 3. So when it moves up, A root 3 by 2. It comes to be A root 3 by 2. So I can put this value in place of OD. So what I can get is BAB is equal to mu naught by 4 pi I by, once again, A root 3 by 2, the 2 moves up, into sine 30 is 1 by 2, sine 30 is 1 by 2, so 1 by 2 plus 1 by 2 is 2 by 2, 2 by 2 is 1, so nothing, so it's 1. So you make a reduction, so this is the value for one side. We can make a much more simpler form, 4 pi 2I by A root 3 into root 3 by root 3. So what the thing happens, you see, it is mu naught by 4 pi into 2 root 3I, 2 root 3I by root 3 into root 3 is 3, so 3A. So we're able to see root 3 into root 3 is 3 into A. So this is the value due to one side of the hexagon. So you know there are 6 sides of the hexagon. So the total magnetic field will be 6 times this value. So what about the total magnetic field B will be 6 times the BAB. So just you're going to multiply this with 6. So what happens, you are able to see 6 into mu naught by 4 pi 2 root 3I by 3A, are able to see 3, 2. So what is the final formula? It is mu naught by 4 pi 2 to 4, 4 root 3I by A. And this is the case for magnetic field at the center of a hexagon. So I'm going to repeat the question. There is a hexagonal loop of a metallic wire of each side A and carries a current I. Find the magnitude of magnetic field at the center of the loop. So already I said, what about the number of sides of a hexagon are 6. What is the contribution as such in magnitude and direction due to one side is same for all the other sides. This means the magnitude and direction is same for each side of the hexagon. So I'm going to make one side value, multiply it with 6 to get the total magnetic field at the center. So how we started? We started from the basic formula for a straight conductor of finite length, mu naught by 4 pi, I by A is the observation distance, here A is OD, and sine phi 1 plus sine phi 2, phi 1 and phi 2, you are able to see 30 and 30. So the only unknown is OD. So how to get OD? OD from this right triangle, tan 30 is AD by OD. So OD is equal to AD by tan 30. AD is A by 2. Tan 30 is 1 by root 3. Simplify, A root 3 by 2. Put it back on the main formula. On reduction, I am getting mu naught by 4 pi 2 root 3I by 3A. This is due to one side AB. So I want the total value at O due to the entire hexagon. So I am going to multiply it with 6. So the final answer comes to be mu naught by 4 pi 4 root 3I by A. I'm going to get into my next question. Two small identical circular coils marked 1 and 2 carry equal currents and are placed with their geometric axis perpendicular to each other as shown in figure. Derive an expression for the resultant magnetic field at O. I'm going to read the question once again. Two small identical circular coils marked 1, 2 carry equal currents and are placed with their geometric axis perpendicular to each other as shown in figure. Derive an expression for the resultant magnetic field at O. And see the diagram, what the diagram says. There are two coils. A, say coil 1 and coil 2, the radius are equal R and R. The location distance is also equal. At O, what will be the net magnetic field due to this two coils? How the two coils are kept? Their geometric axes are perpendicular to each other. So let us check the direction rule. So I'm going to speak for coil 1. Can you use the right rule, right hand thumb rule? So you are able to see the coil is like this. The current is flowing like this. So the magnetic field will be along OA. What I can do? Obviously it's a 2D. If I'm going to assume a 3 dimension, the coil will be like this. So the current is flowing like this. The thumb will indicate the direction of magnetic field. So this means the magnetic field acts along OA. The magnetic field acts along OA. So I'm going to mark this field as B1. I'm going to mark this field as B1. Similarly, you check the same rule for coil 2. You are able to see this is in the plane. You are able to see very clearly the current is flowing as per the fingers. The thumb will indicate the direction of magnetic field. So you are able to see it will be upwards, and I'm going to mark this will be the direction of B2. So this is B1 vector and B2 vector, and very correctly you know how to get the resultant from the parallelogram law. The diagonal will represent the resultant magnetic field. Then I'm going to mark it as B vector. So what is the formula for resolution? You know, that is B will be under root B1 square plus B2 square. Obviously already we studied what is magnetic field due to a current carrying circular coil at a point on the axis. What is the formula? Obviously it is a diagram like this. So this is the location point. If a current I flows, what about the magnetic field at a distance, say P? You know B is equal to mu naught by 4 pi 2 pi I A square by A square plus x square to the power 3 by 2. Obviously this distance is x and the radius here is A. You are going to make a little bit modification. Here the radius is r, but the location distance is x only. So I can use this formula for B1 and B2. Magnitude wise they are same. So what I can write is, obviously you can take the things common. It will be mu naught by 4 pi is existing for both. 2 pi is also existing for both. I is same for, I'm going to assume same current is flowing in both the coils. Same current flows in both the coil. So I is also same. Radius is also same, so r square by r square, the distance location is also same, so everything is same. So what I can do is, only thing that is left is 1 plus 1. So ultimately the value comes to be root 2 times the value of the 1, that is mu naught by 4 pi 2 pi I r square by r square plus x square to the power 3 by 2. So once again I am going to repeat the question. What the question says, there are two small identical circular coils marked 1, 2 carry equal currents and are placed with their geometric axis perpendicular to each other as shown. Derive an expression for the resultant magnetic field at O. Once again, what is the magnetic field due to a flow of current I in the coil I1 acts along OA? I'm going to mark it as B1. Similarly, due to the flow of current I in coil 2, what about the direction of magnetic field is B2? It is acting outwards. So what about the net magnetic field can be obtained by parallelogram law or a resolution? B comes to be under root B1 square plus B2 square. So what is magnetic field along the axial line is mu naught by 4 pi 2 pi I A square by A square plus x square to the power 3 by 2. Replace A with R. All the things are common. So what I'm going to get is root 2 times this value. So this is one of the common questions that is usually repeated in the board examination. Now let us get into some short answer type questions that are usually asked in the board examination. So one by one we are going to get into the question. So my first question is the source of magnetic field analog to the source of electric field? So what the question says, is the source of magnetic field analog to the source of electric field? So you should know. What about the source of electric field is an electric charge. You are able to see what is the source of electric field is electric charge, whereas what is the source of magnetic field is not a magnetic charge. You should know the source of magnetic field is not a magnetic charge, rather it is a current element. So what is our answer? No. So is the source of magnetic field analog to the source of electric field? The answer is no, because for the source of electric field it is an electric charge, whereas the source of magnetic field is not due to magnetic charge, and the answer is no. So I can get into my second question. A conductor carrying current is placed somewhere. A conductor carrying current is placed somewhere. So what is the magnitude and direction of the field? What is the magnitude and direction of the field due to a small part of the conductor at a point near it? I'm going to read the question once again. A conductor carrying current is placed somewhere. What is the magnitude and direction of the field due to a small part of the conductor at a point near it? So obviously the question seems to be a little bit twisted one, but ultimately they are asking Biot-Savart law. Are able to see what is Biot-Savart law? Biot-Savart law was used to find magnetic field due to a current element. The same thing they are asking in the question. So just you write the mathematical formula for Biot-Savart law. So what about the mathematical formula for Biot-Savart law? What is the magnitude they are asking? Magnitude is dB. In vector form they are asking, so I can write it as mu naught by 4 pi I dl vector cross r cap by r square. This is the answer for the question. Once again, a conductor carrying current is placed somewhere. What is the magnitude and direction of the field due to a small part of the conductor at a point near it? So magnitude wise and direction wise, this equation clearly establishes the magnetic field due to a current element. I'm going to get into my third question. What is the SI unit of magnetic permeability of free space? What the question says, what is the SI unit of magnetic permeability of free space? You know what is magnetic permeability? It is creeping in the Biot-Savart law expression. So what was Biot-Savart law expression is dB is equal to mu naught by 4 pi I dl sine theta by r square. This was the formula. They are asking what is the SI unit of magnetic permeability. They are asking the unit for mu naught. So make a formula for mu naught. Mu naught comes to be, mu naught becomes, it becomes magnetic field, dB is magnetic field, into the distance square, that is r square, by current, that is I, into length. Sine theta has no unit, so be careful while shifting. I want the unit for mu naught. So mu naught will be dB into r square, that is dB is magnetic field, r square is distance square. This I and dl moves to the denominator. I is current and dl is length. So just you put all the values. What is magnetic field measured in? Tesla. Magnetic field is measured in Tesla. Distance square is meter square. Unit for current is ampere, and for length is meter. Once one meter cancels off. So what I'm going to get is Tesla meter ampere inverse. The unit becomes Tesla meter and ampere inverse. So what is the SI unit of magnetic permeability of free spaces? I can say Tesla meter ampere. Yeah, Tesla ampere inverse into meter. With this, I'm going to get into my fourth question. Does a current carrying circular coil produce a uniform magnetic field? Once again, I'm going to repeat. Does a current carrying circular coil produce a uniform magnetic field? Obviously, the question has a little twist. What they are saying, whether the magnetic field will be uniform when a current flows through a circular coil? The answer is no. At everywhere, the magnetic field pattern will not be uniform. However, we can assume that, we can consider that the uniformity exists at the center of the circular coil. What about the uniform magnetic field? It can be considered to be uniform only at the center of the circular coil. Once again, what the question says, does a current carrying circular coil produces a uniform magnetic field? The answer is no. However, it may be considered as uniform at the center of the circular coil. I'm going to get into my fifth question. What the fifth question says, what is the effect of increasing the number of turns on magnetic field produced due to a circular coil? Once again, what is the effect of increasing the number of turns on magnetic field produced due to a circular coil? So let us get into the formula for magnetic field at the center of a circular coil. You know what is magnetic field at the center of a circular coil? Already we know B is equal to mu naught by 4 pi 2 pi I by A. A is the radius of the circular coil. Now what they are asking, if we are increasing the number of turns, This means n is increased. So you know this is for one turn. If there are n number of turns, I'm going to multiply it with n. So we're able to see if n increases, the magnetic field also increases. So what is the effect of increasing the number of turns on magnetic field produced due to a circular coil? Basically it increases with increasing number of turns. I'm going to get into my sixth question. What the sixth question says: looking at the circular coil, you are looking at the circular coil, the current is found to be flowing in anti-clockwise direction. The current is found to be flowing in anti-clockwise direction. You are going to predict the direction of magnetic field at a point on the axis of the coil, on the same side as the observer. Once again, I'm going to read the question. Looking at a circular coil, the current is found to be flowing in the anti-clockwise. The current is found to be flowing in the anti-clockwise direction. You are going to predict the direction of magnetic field at a point on the axis of the coil on the same side as the observer. So already you know we did it number of times. Obviously it's a very simple question. So what about the direction of magnetic field? Magnetic field will be perpendicular to the plane of the coil. It will be perpendicular to the plane of the coil, and you know it is directed towards the observer. The number of times we are using this rule. What about the direction? It will be perpendicular to the plane of the coil and it's directed towards the observer. I'm going to get into my next question. What kind of magnetic field is produced by an infinitely long current carrying conductor? So what the question says, what type of magnetic field is produced by an infinitely long current carrying conductor? To be very sensitive with the question, they are not asking about the magnitude of the magnetic field, they are not asking the direction, but they are asking the pattern or the kind of magnetic field produced by an infinitely long current carrying conductor. So already I think in 10th also you studied. What about the pattern of magnetic field around a current carrying conductor? It will be of concentric circular loops. You are able to see it will be of concentric circular loops with the conductor centered. Obviously the conductor will be passing through the center of those concentric circular loops. So once again, what kind of magnetic field is produced by an infinitely long current carrying conductor? It will be of concentric circular loops in a plane perpendicular to the straight conductor. It will be in a plane perpendicular to the straight conductor. Now, some most important question. What about my 8th question says, give two similarities, you are going to give two similarities between Biot-Savart law for magnetic field and Coulomb's law for electrostatic field. So the question has a little bit twist. You are going to establish two similarities between the magnetic field due to Biot-Savart law and the electrostatic field due to Coulomb's law. So what are the two similarities I can say? Both the law apply to the fields, both the law is applicable to the field which obey inverse square law. What is the first similarity I am going to say? Both the law is equally applicable to the field which obeys inverse square law. This is the first similarity. Number 2, both the law is applicable to the field which obeys superposition principle. So obviously if the field is going to obey inverse square law, they are equally applicable for both magnetic field as well as electric field. Similarly, if they obey superposition principle, then also they are equally applicable for Biot-Savart law as well as Coulomb's law. So what are, once again I am going to read the question. Give two similarities between Biot-Savart law for magnetic fields and Coulomb's law for electrostatic field. So what the answer says, both the law apply to the field which obeys inverse square law, number 1. Both the law apply to the fields which obey superposition principle. I am going to get into my 9th question. It is a similar question, but the question says, give two differences. You are going to speak two differences between Biot-Savart law for magnetic field and Coulomb's law for electrostatic field. The last question says the similarity, whereas this question asks the difference between the two fields. One due to Biot-Savart law for magnetic field and another Coulomb's law for electrostatic field. So the very first difference I can say, Coulomb's law applies to the field produced by an electric charge. Already we know Coulomb's law is applying to the field produced by an electric charge, which is a scalar quantity. Whereas Biot-Savart law applies to the field produced by a current element. You know the source of electric field is an electric charge, which is a scalar quantity, whereas the source of magnetic field is a current element, which is a vector quantity. This is the first difference between the magnetic field due to Biot-Savart law and the electric field due to Coulomb's law. What about the second difference is the direction of the electric and magnetic field. You are able to see what about the direction of electric field is along the line joining the charge and the observation point. What about the direction of electric field in case of the Coulomb's law? The electric field is along the line joining the charge and the observation point. Whereas if I am going to assume into Biot-Savart law, the direction of magnetic field is perpendicular to the plane containing the current element and the observation point. Whereas the electric field direction is along the line joining the charge and the observation point. What about the direction of magnetic field is in a direction perpendicular to the plane containing the current element and the observation point. With this, I am going to end my session. Take care of yourself.